Let's work through this related rates problem together. So here's the situation. A spherical balloon is inflated with gas at a rate of 20 cubic feet per minute. How fast is the radius of the balloon increasing at the instant when A, the radius is 1 foot, and B, the radius is 2 feet? Okay, so let's follow the steps we've established for solving related rates problems. The first step is always to read the problem carefully and make sure we understand the situation. And then the second step is to draw a picture and label it. And we want to label things that never change as numbers and label anything that changes as a variable. So let's make sure, we'll kind of do these first two steps together. But let's make sure we understand what's happening in this problem. So in this problem, a balloon is being inflated with gas. And so that gas going into the balloon is causing the volume of the balloon to increase. And as that happens, in turn, the radius of the balloon is also increasing. So we're kind of exploring the relationship between the way the volume is increasing and the radius is increasing. And so in this case, both the volume of the balloon and its radius are variables. Those are both things that change over the course of this problem, over the course of the balloon being inflated with gas. So for this particular problem, the picture is really not that interesting as opposed to maybe one of the more complicated related rates problems you'll see. But here we have our balloon, and I've labeled its radius as little r. And we can use the variable v to stand for volume. Okay, so what's the next step in the related rates process? Well, we want to think about what rates we know and what rates we're trying to find, and then associate those rates with the variables we've established so far. Okay, so let's think about what we know. So we're told that a spherical balloon is being inflated with gas at a rate of 20 cubic feet per minute. So that 20 cubic feet per minute is the rate of change of the volume of the balloon. So then I would write dV dt equals 20. This is something I know. Okay? That's the rate I know. What else? Well, what we're asked is how fast is the radius of the balloon increasing? So what is that? That's dr dt. And that's what I'm ultimately going to look for at certain points in time when the radius is 1 foot and when the radius is 2 feet. Okay, so now I know what I know, and I know what I'm looking for. So what's the next step? The next step is to find a relationship between the variables in the problem, and then to write down an equation for that relationship. Okay, so this is usually going to depend somehow on the geometry of the problem. So in this case, I have a spherical balloon, so that's a key word there, spherical balloon. And I'm looking for a relationship between volume and radius. So what that's going to be in this case is actually the formula for the volume of a sphere, which is volume equals 4/3 pi r cubed. So this gives me the relationship between the volume of the balloon and the radius of the balloon. Okay, so what's the next step? The next step is to look at the equation we've just written and eliminate variables from the equation that I am not interested in. So in this case, I know about the volume of the balloon, and I'm looking for the radius. So v and r then should be the only variables present in my equation. And in this case, they are. This is a relatively simple related rates problem compared to some of the later ones we'll see. So in this case, there's no extra elimination we have to do. But if for some reason we had an additional variable in our problem besides the v and the r, we would want to come up with some method for eliminating that variable. Okay, but now our equation is good. So what's the next step? Well, the next step is to take the derivative with respect to time. So let's go ahead and do that. Okay, so what I really want to do then is take the derivative with respect to time of both sides of the equation, and that's going to require me to use implicit differentiation. So here, both volume and radius should be thought of as functions of time. Both of these things depend on time, right? The volume changes with time and so does the radius. So we need to use implicit differentiation and the chain rule when we take the derivative. So then, keeping that in mind, the derivative of v with respect to t, I'm going to write as dv dt. Okay, what about the right-hand side? Well, I'm taking the derivative of this expression with respect to time. Okay, so I'm going to start as I normally would. So I have this r, and r I'm thinking of as a function of time, but I start by taking the derivative of the outer function, if you want to think of it like that. So I bring down the 3 like this. But then, since r is a function of time, I need to remember to multiply by its derivative, which is dr dt. Okay, and then I can clean this up a little bit. So 4/3 times 3 is 4. So I get 4 pi r squared dr dt. And this is my derivative with respect to time. Okay, so what do we do next? Well, now I'm at the point where I can start plugging some values in. So the next step, if you're following along with the recommended steps, the next step says to plug in values that never change. So this is usually referring to the rates that we know. So for example, I know that dv dt equals 20. So I can go ahead and plug in that 20. And I would get this. Now, I know that I'm ultimately looking for dr dt, so I'm going to go ahead and solve this relationship for dr dt. So if I do that, I'm going to get dr dt equals 4 pi r squared over 20, which I can reduce to pi. Sorry, I did that the opposite way from what it should be. So I should have written there 20 over 4 pi r squared. And then I can reduce that to be 5 over pi r squared. Okay, so I have dr dt equals 5 over pi r squared. Now, if you remember what we were asked for in the original problem, we were asked for dr dt, the rate at which the radius is changing, at two specific instants. First of all, at the instant when the radius is 1 foot, and second of all, when the instant at the radius is 2 feet. So this is what we sometimes call particular moment information, right? I'm looking for a rate of change at a few particular moments. So you want to be careful to never plug in the particular moment information until this very last step. Okay? So, and kind of the reason for that is if you look here at this relationship here, dv dt equals 4 pi r squared dr dt. This gives me a relationship between the way the volume is changing and the way the radius is changing. And they depend on each other, right? And if you notice, r is a part of this equation. So the way those rates of change depend on each other, r, the value of the radius, is tied up into that relationship. So I don't want to plug in any particular value of r until the very end. So that might clear it up a little bit for you, hopefully. But anyway, the point is wait until the end to plug in that particular moment information. Okay, so what do we want to know? First of all, we want to know when r equals 1 foot. Okay, so let's go ahead and figure that out. So dr dt equals 5 over pi r squared. And when r is 1, then this is going to give me 5 over pi. And the units on this would be feet per minute. We want to be consistent with the original units. And then the other piece of information we're asked about is when r equals 2. Okay, so once again, we're just plugging in here. So 5 over 2 squared would be 4. So this would be 4 pi feet per minute. All right, and these are our final answers. These were the rates of change that we were looking for.